Hello everyone, here with another video on CalcPlot3D. This time we are going to focus on double integrals over general regions and even polar regions. So basically not going to be focused as much on Riemann sums. We'll just very briefly talk about what we can do with Riemann prisms here in CalcPlot3D, but mostly focusing on how to look at volumes under surfaces and above things that are not rectangles. So again, we are going to go down here and add a region. And we'll start with just the default one. So here, right, it naturally sets you as y equals stuff in terms of x for your 2D region. And then the 3D region, it gives you in terms of basically z, right, your f of x, y. And so here it's just starting at the xy plane, z equals 0, and going up to the bottom of your bowl shape or paraboloid x squared plus y squared. So if I just go ahead and click here, you can see the region here is a parabola, and then we are below our bowl shape. So this is the volume that we would be looking at if we were doing the double integral over this 2D region. So if you're focusing solely on the bounds and like moving from dy dx to dx dy, stuff like that, all you really care about is the 2D picture over here, which is also stuff you could do in Desmos. However, if you do want to see what volume you're talking about, picture things in 3D, then CalcPlot3D can do a little bit more because it can show you this picture on the right. Additionally, you can kind of check yourself if you're actually computing your double integral and say, in this case, right, you'd get a positive number because we're seeing all of our volume is above the xy plane and below our surface. Whereas I'm not sure what this would give you without calculating, because if I do x squared minus y squared, I have some volume that is above, and then some volume that is below the xy plane that would be like subtracted away, because we're thinking of net volume. So this one, right, you'd have to kind of see what you calculate, and then does it match your intuition from the picture. So this is something extra you can kind of do in CalcPlot. I'm going to focus primarily, though, on just what you can do with different regions. So let's start with just this standard format or setup that it has, and we're going to look at several different semicircles, okay? Or I guess the same semicircle several different ways. So I'm going to do the semicircle of radius 2 on the right side of the xy plane here, so basically with x being positive. So in this case, x will be going from 0 to 2. And if I just do square root of 4 minus x squared, this only gives me the quarter circle. To include the bottom, I want to do the negative square root as well. And this is gross on the page, so I'm going to zoom out once. And now you can see we're above a semicircle and below the bowl, so this is the volume that we're talking about. And you can see that this is a little bit complicated, right? My x bounds are really nice, but because I'm using a curve here and a curve here, basically this doesn't pass the vertical line test, I have to use two different kind of nasty functional bounds in terms of y. So this is maybe not the preferable order, dy dx. Maybe you'd want to do dx dy. Well, you can just switch to x equals f of y. And so my left bound for x is going to be 0 still, but then my right bound will be the square root of 4 minus y squared. And then my y should go from negative 2 to 2. And so I get that same semicircle, but now I have a little bit simpler bounds because I just view my left as being a vertical line, constant bound, and then only my right bound is requiring this kind of nasty function with the square root of 4 minus y squared, right? So this is a little bit simpler, and so sometimes, right, if you have things in terms of y or you want to get them in terms of y, you can use this x equals f of y button. Something else you can do if you click on rect over here, so this is for rectangular coordinates, it will switch to polar coordinates. So this is a semicircle. It kind of naturally lends itself toward polar coordinates, right? And so I said radius 2, so we do want to go 0 to 2. This is already nice with the default. But our angle, we want something like negative pi over 2 to pi over 2 to get this, right? Or You could go farther, right, and do something like 3 pi over 2 to 5 pi over 2 if you wanted, and you would get the same region. So in this case, right, we have all numerical bounds. This is kind of the simplest route to take because semicircles naturally tell us, hey, we should probably look at polar coordinates here. So you can do that. It does allow you to change in terms of theta equals something in terms of r if you ever run into that. But most of our examples, we're just really thinking of numerical bounds for these. So as long as you know your unit circle, you can mess with things pretty easily here, right? So if I wanted like a quarter circle from here to here, right, I could do something like 3 pi over 4 to 5 pi over 4, right? And so if I want to change my radius, maybe I want an annulus, right? Maybe like a washer, you can do 1 to 2. So you can do a whole bunch of different regions, and you can kind of decide whether polar or rectangular coordinates are going to make life easier. So hopefully this helps you see what you can do in CalcPlot3D. Again, the stuff on the left you can do in Desmos, but if you do want to see what's happening in 3D, then CalcPlot3D can do all of the same things as Desmos and a little bit more. So hopefully that helps, and thank you for watching.